All right. Welcome. Today, we're going to tackle one of the most fundamental and, frankly, one of the most profound rules in all of nature. I'm talking about the second law of thermodynamics. And trust me, it governs everything, from the coffee you're drinking right now to the ultimate fate of the entire cosmos. So let's just dive right in with a simple question. Picture this. A cup falls off a table. It shatters into a million pieces. Total mess, right? We've all been there. But have you ever seen the reverse happen? You know, the little pieces suddenly decide to fly back together, leap off the floor, and perfectly reform the cup? Of course not. It sounds ridiculous. But the real question is, why? Okay, and here's what's so fascinating. The first law of thermodynamics, the one that says energy is always conserved. You can't create or destroy it. That law has zero problem with the cup reassembling itself. The energy is all there. So technically, it should be possible. But then the second law steps in and just says, nope, not going to happen. This is the law that basically gives the universe a one-way street sign. So to really get why, we need to start with the simplest, most basic expression of this law. And it's all about something you experience every single day: how heat moves around. I mean, this is something you already know instinctively, right? You put a hot coffee mug on a cool table, the mug gets cooler, the table gets warmer. Heat always flows from the hotter thing to the colder thing. It's a one-way trip. It never ever just decides to flow the other way all on its own. So back in the 1850s, a German scientist named Rudolf Clausius basically wrote this down officially. He pointed out that, look, you can make heat go from cold to hot. I mean, that's literally what your refrigerator is doing right now. But it's not happening by itself. You have to force it. You have to plug the fridge in and add energy. Left to its own devices, the flow is always downhill, from hot to cold. Okay, so this whole idea, this inescapable one-way direction for pretty much everything in nature, it's all wrapped up in a really powerful and, yeah, often misunderstood concept. And that concept is called entropy. So what is entropy? Well, you can think of it as the universe's official measurement of disorder or randomness. Here's the key rule. While energy has to stay the same, the total entropy of an isolated system can only go up. It can never, ever go down. So for something to happen spontaneously, for it to be allowed by the universe, it has to increase the total amount of disorder. And once you know what to look for, you see this everywhere. Think about an ice cube in your drink. That's a nice, ordered crystal structure. It melts into a puddle of jumbled, disordered water molecules. Or a drop of ink in a glass of water. It starts as a concentrated dot and spreads out into a random mess. And yep, the classic example, your room. It's so much easier for it to get messy than it is to keep it clean, right? That's entropy in action. All these things are irreversible because they're all moving towards more disorder. Now, you might be thinking, wait a minute, I clean my room, I build things, I create order. And you're right. But here's the catch. To create that little pocket of order, like building a house, you have to create a ton more disorder somewhere else. Think of all the energy burned, the materials processed, the heat released. When you add it all up, the disorder you created in the universe is always way more than the order you created in that one spot. The universe's total entropy always goes up, no exceptions. And this law isn't just some abstract idea. It sets very real, very hard limits on what we as humans can actually build. You know, for centuries, the ultimate dream for inventors was the perpetual motion machine. One of the cleverest ideas was something that could just pull heat out of the ocean. I mean, the ocean has a staggering amount of thermal energy in it. So why can't we just build a machine that sucks that heat up and uses it to power a ship forever? Well, the second law of thermodynamics is the reason why. It's not a technology problem, it's a fundamental physics problem. To get useful work out of heat, you don't just need heat, you need a difference in temperature. You need heat to flow from a hot source to a cold sink. Trying to get energy from the ocean is like trying to sail a boat when there's no wind. The energy is there, but there's no flow, no gradient, so you can't do any work. Lord Kelvin really put a fine point on it. You just can't build an engine that's powered by making its environment colder. You always need a hot place and a colder place to dump some of that waste heat. That's why no engine is ever 100% efficient. And that's not because our engineers aren't smart enough, it's because the universe literally won't allow it. Okay, this brings us to what is maybe the most mind-bending consequence of this law. The reason a cup shatters and doesn't put itself back together is the very same reason you can remember yesterday, but you can't remember tomorrow. It's called the arrow of time. Just think about that for a second. Most of the basic laws of physics, like gravity and motion, work perfectly fine forwards or backwards. A video of a planet orbiting the sun looks normal whether you play it forwards or in reverse. But we only experience time moving in one direction. So why? The answer is entropy. The universe as a whole is moving from a state of low entropy to a state of high entropy. The forward direction of time, that's just the direction of increasing disorder. This timeline of the cosmos really drives the point home. The universe began in this incredibly hot, dense, and surprisingly very orderly low entropy state at the Big Bang. And for the last 13.8 billion years, its total entropy has just been going up and up and up. Stars are burning out, energy is spreading thin, and the ultimate theoretical end of this journey, it's something called heat death. A final state of maximum entropy where everything everywhere is the exact same temperature. And because there's no heat flow, nothing happens. Ever again. So you see, the second law is so much more than just a rule about messy rooms or inefficient engines. The astronomer Arthur Eddington once said that if your new theory goes against the second law of thermodynamics, there's just no hope for it. It's that fundamental. It is the law that tells us why time flows forward, why shattered cups stay shattered, and why the universe itself has a story with a beginning, a middle, and an end. It truly is the universe's one-way street, guiding everything everywhere, from a state of order toward an inevitable and final state of quiet disorder.